We are Computer Engineering Team 3, and this is our project Rock Chomp, Smarter Snacking, Jayhawk Style. I am Shayna Weinstein, our project and hardware lead. We have Gage Weaver, our machine learning lead, Shaden Wright, our data lead and front-end support, and Abel Herzberg, our software lead. A bit of a project overview. So we designed a smart vending machine with personalized recommendations, which adapts to dietary restrictions and allergens, fitness goals, time of day, and user preferences. We built this project using a milestone-based development process, and our final system delivers real-time adaptive suggestions to improve users' experience.
Going to go more into the background and purpose behind our project. We felt that snacking as a whole, whether it's through a vending machine or anything that you have yourself, has become rather impersonal as of late, so we wanted to change that a little bit. Our machine is designed to give personalized recommendations for a multitude of goals, whether that's allergy or dietary restrictions, or you just finished a tough workout and you need some protein to get those macros for the day. That machine can take that into account, as well as time of day awareness for potential breakfast, dinner, or lunch options. And then to kind of go into the milestone approach that Shannon touched on previously, we have 3 milestones here. Milestone 1 was when we received all our parts. We wanted to validate that they were working properly and could work separately as a whole before we integrated them together in milestone 2, which was a complete board schematic, which would be duplicated on 3 levels to complete our final milestone, having the whole vending machine working properly in the cabinet design.
And then here's a look at our Gantt chart timeline. This is kind of how we broke up scheduling all the different stages of our project. We started working on this at the end of last semester when we did our research and component selection stages. And as Shayton mentioned, we've worked about every month to deliver at least 1 milestone. And then over the past few weeks, we finally finished up the project with our board fabrication and integration and testing.
So a bit of our theory for our hardware side of things. So our smart vending machine integrates embedded systems, control theory, and recommendation algorithms to deliver personalized product suggestions and automated dispensing. So there's a multi-controller architecture here where we have a Raspberry Pi 5, which handles all of the high-level decision-making and the recommendation logic, while a Raspberry Pi Pico manages low-level real-time control. There's a Pico on each board, which is replicated on each level. So each Pico actually controls 2 different motor drivers, which then control 2 different stepper motors, which then dispense 2 different items. And it is a closed-loop decision architecture where we go from user input to filtering and recommendation to actuation, leading to dispensing the item for the user.
And then a little into the machine learning aspect of the project. So starting off with the background on tree-based gradient boosting. So tree-based gradient boosting is a machine learning method where trees are built sequentially, and this allows later trees to learn from mistakes that the previous trees have made, which leads to higher accuracy and more efficiency. And this functions by using residuals. So when a tree makes an incorrect prediction, it passes a value known as the gradient to the next tree so that it can know how far off it was. And we specifically chose XGBoost for this project because it applies L1 and L2 norms to reduce overfitting. So this is pretty crucial on a small data set like ours. It applies functions to the weights the model learns to shrink them, to take up less space, and as well to enforce sparsity. And then we also process the trees in parallel to speed up training, and this is important for a multi-core Raspberry Pi 5.
So for the implementation of the hardware side of things, here is the basic schematic of our project, which then leads to the PCB design. This is the PCB design that was replicated on all 3 levels, showing that Pico in the middle, which then goes out to 1 motor on either side.
And here's a look at the pin layout for the 2 boards, the Raspberry Pi 5 as well as the Raspberry Pico. And on the next slide here, we'll show you kind of how those pins were laid out. The first 2 pins from the Raspberry Pi 5 there in the blue went to the Raspberry Pi Pico. These were our transmitting and receiving pins for communicating between those 2 boards, as Shayna mentioned, for the actual dispensing. And then we connected pin number 6 on the Raspberry Pi 5 to common ground. And then for the rest of them are the Pico connections to our motors for the pulse, direction, and enable, as well as the limit switches, and then finally that pin 39 for the step-down voltage.
So a couple hardware design constraints that we set for ourselves. So we wanted all of our hardware to fit in the cabinet itself, which led to only 6 motors for dispensing, so 6 different items. We had to have a way to dispense the food without opening the machine itself because that would pose both physical risks as well as losing our inventory. Our motors had to have enough power to dispense the food, whatever food we wanted to dispense, no matter the weight. There had to be enough direct voltage to power the motor, but not fry the microcontroller. And as well as the LEDs needed to be powered with a 5-volt external source. And the product had to be dispensed based on user input. We couldn't just dispense whatever product we wanted at whatever time. So here's our hardware implementation. On the top left, we have the board soldered with all of our components. On the right-hand side is the middle level of our machine, which shows our connections from the Raspberry Pi 5 on the right of the cabinet up at the top, which then goes into a proto board, which disperses the signals out to each board on each level for rotation, and then the 2 motors with their respective coils, and then a final look at our illuminated level with all of the items we were going to dispense. In this case, our Nerds gummy clusters. Some challenges we ran into on the hardware side included needing to have all of the hardware wires fit in the cabinet in terms of visual appeal, because as you saw in the previous slide, it looked a little jumbled. However, we wanted to make sure that you didn't see the wires on the outside and to prevent any wires from being disconnected when moving the actual cabinet. The hardware had to be replicated on all 3 of the levels, so there needed to be more soldering time. We did not have access to the Eagle board design software anymore through KU, which is what we had originally learned when learning to design PCBs. So I needed to learn KiCad as an alternative. We had the PCBs are coated in copper, so that's metal on a metal cabinet. So we needed to have an intermediate plexiglass layer to prevent any shorting of the wires and signals. And then the direct signals from the Pico itself weren't controlling the motor signals because our Pico voltage that went out from the data signals were 3.3 volts, and you needed a 5-volt input signal for the motor driver. So I ended up using the 2N2222 transistors and 1K resistors to step the signal voltage up to that 5 volts.
Here's a diagram of our software implementation. So we have 3 main sections here along with our assets, which is just essentially the images used for the candy. So starting with the back end, we have our app.py, and this controls all the Flask routing. So this is how our machine learning model is able to pass data between different endpoints, as well as send the signal to dispense and everything like that. We have our db.py, which is helpers for interacting with the database. That way we aren't showing stale data on the front end. We want to make sure users are seeing the live data, as well as reco.py, which is where we handle all the recommendations. This is the machine learning model, the allergy avoidance, everything like that is contained in there. We have our front end section, which contains both the admin UI and the main kiosk UI. The admin UI is essentially just for the machine owner to restock everything, and the kiosk UI is what users actually see. And then the database section has our tables to store everything, as well as JSON documents for some of the allergy-related things. And here's some of the constraints that we worked upon while working on the software. So firstly, we wanted to have a touchscreen first layout, which means our software design must scale well down to a small touchscreen device and be easily interacted with by touch instead of keyboard and mouse. Like I said earlier, we need to make sure the state is live. We don't want to be showing users candy that are out of stock as in stock. The ML resources was also a challenge. Since the model must run locally for both privacy and performance, we chose XGBoost for this because it can leverage the multiple cores of the Raspberry Pi. And then lastly, our software can't bloat the limited resources of the Pi 5 to ensure it stays smooth. And here's a video of our software implementation. So you'll see here that you start and you come to a login screen, And we'll go ahead and enter our KUID here. And then once we enter it, we'll be taken to the main page. So here you can see just a generic recommendation profile before we've customized anything. And you can see once you click on a candy, you can see any of the related information that you might want. So here I'll enter that I'm allergic to peanuts and I want to keep kosher. So this limits the options, and you'll see that it gives warnings to the users for products that don't fit. So I went ahead and bought a bag of potato chips there, and will simulate me coming back to the machine another time where it gives me a survey, and this will update the rankings based off of how I respond in the survey.
Kind of going to some of those software challenges that we faced when working with those design constraints. We knew that the design needed to be atomic, meaning that it has to either work perfectly or fail, because when you're working with a vending machine and transactional occurrences, you can't have a user give us money and then not give them their product. So we needed to ensure that the machine would either break completely or work completely. That way that nobody was getting shorted in terms of product, and that the machine would work properly all the way through use. And then we need to do a custom Chromium launch as well. Because the app is hosted on the touch screen, it can be escaped if not done properly. So the user could get out of the user interface and potentially you navigate the web or do anything else on the Pi 5, which we don't want, obviously. And then we also needed to ensure that our machine learning approach was done correctly. Because we were working with the Pi 5, as Gage mentioned, we needed to choose an approach that would be accurate but efficient as well, so that the machine wouldn't be slowed down by the hardware constraints.
And then here's a look at a few of the technical standards we used throughout this project. The first two, the RS-232 and the JES-D8, were used for our communication between the Raspberry Pi 5 and Raspberry Picos. And then we also used step and direction interface, which was for our motors as well as the drivers themselves. And then we also used IEC protocols for the power supply, our step-down voltage circuits, as well as our transistors. And then finally, we followed IEEE embedded systems practices throughout the build stage of the project.
And it was important to test out our machine before fully implementing it. So here was the test plan for our hardware. So first we tested it by creating an out-of-the-box build. This is so we could test all the hardware before actually mounting it into the vending machine. And this basically involved setting up our circuit and using the Raspberry Pi 5 to drive the motors without the recommendation system and the UI, just to kind of test it in an isolated environment. And then in the full vending machine, we created 3 instances of the same vending mechanism and tested each of these before actually implementing them into the hardware. And then the test plan for the software, we tested this as well before implementing it with the hardware. So first, we tested that the software could be run outside of the machine on any laptop or Raspberry Pi. This allowed us to just test without actually having to have all the stuff mounted on the machine. And then once the hardware was fully integrated, we slotted in the Raspberry Pi 5, which basically acts as a monolith. So it runs the model, calls the dispensing functions, and runs the UI all on the touch screen. And then we tested dispensing all 6 of the products via the touchscreen, and the user recommendations were tested with different profiles to ensure accuracy.
And then in terms of our performance evaluation, we had a few metrics we wanted to ensure we hit in order to call this project successful. The first and most important was that we reliably dispensed our snack items without damaging them. This was a common occurrence that we all agreed back in our research stage, that we'd all encountered issues with other vending machines, and we wanted to make sure ours didn't have the same issue. And then secondly, we wanted to make sure that we got the ML recommendation correct, especially for the allergies and dietary restrictions part, since the health of our customers is a huge concern for us. And then finally, we also wanted to make sure we communicated all of those smart aspects that we added to the vending machine, such as that ML model, in a way that isn't confusing or frustrating for our users, because if it's frustrating for them, they won't want to use the machine. And then also we have to make sure we implement user feedback to fine-tune that model and give even better recommendations to users in the future.
So to kind of break down some of our costs here, you can see all the parts that we ordered and worked with. Not all made it into the machine or served a functional purpose, but this was the initial layout that we thought we would be working with a total of 47 orders placed and a total cost of around $1,400.
Reliability was a huge concern for us as well. So here are a few of the things that we've noted for the reliability in the future. Mainly that if we have a larger student body integration with more machines and more KUIDs used throughout the process, we might run into issues with the recommendation model slowing down since it's all hosted locally on the Pi. This would be something we could look into for potentially using a cloud-based solution in the future. And then finally, the only other concern with reliability is all the mechanical parts inside the machine. Most of these have actually quite a long duration of life before the failure, but the DC motors and the dispensing actuators in particular have the lowest cycles, so those would need to be replaced most often. And then in terms of the risk and safety as well as health and environment, first for the safety, we wanted to make sure we put the locks on the cabinet to prevent users from interacting with everything inside the machine. Obviously, there's a lot of moving parts in there and a lot of electrical systems that could pose risks to users if they were to touch them accidentally. And then also we had to make sure that we routed the wires in a way that wouldn't create hazards. Since all the items can be dropping from shelves on different levels, we want to make sure that they didn't snag any wires and cause any issues with the electrical systems. And then we also cut holes in the base cabinet that we ordered, so we had to kind of sand down those edges to make sure that when someone is interacting in the machine, such as the owner to restock, that they don't have any cuts on those sharp edges. And then we also had to make sure that we were very strict with our allergy and dietary restrictions, warning users extra times before they were to purchase anything that's on their allergy list so that we don't have any health concerns there. And then finally, for environment, we don't see many potential risks environmentally with this machine since it doesn't create any pollution or waste itself. The only real waste can come from the wrappers on the products, but that will be thrown out by the users after their use.
So to kind of go into the conclusion of what we feel we did best and maybe some of the limitations of the machine, we're really confident in the workmanship that we put into the machine with the workmanship or the wiring, and the board build itself was done really well and in a way that we feel is beneficial to the machine's success and admin usage. And the outer design looks nice as well, and the user interface is very strong in that we convey those smart aspects that Abel mentioned earlier while also making it very intuitive to use and not confusing for the user. Some of the limitations we had working with the cabinet and our vending machine is definitely one of the bigger limitations, considering that it limits our inventory, how many items we can have, as well as the style of design that we needed. For a traditional vending machine, item shelves are usually sloped towards the user, but in our implementation, we had a horizontal approach, which kind of led to some dispensing problems every now and then with items not falling properly. And then for some possible improvements that we were considering in the future, if we had a little more time, or if we wanted to mass produce the machine, we would definitely want some more wiring housing and house the devices a little more less visually, so that it's harder to interact with for any person restocking the machine. That way it would prevent the machine from getting broken or anything like that. And then we maybe want some 3D printed components such as funnels, as I mentioned, with the products not dispensing properly all the time. It would help increase the reliability that the products do make it to the user when they're purchased. And then, as I mentioned, with the smaller vending machine cabinet that we used, maybe expanding the size of the machine to support more inventory, or just a more traditional vending machine design as well.
And here's a full demo running through the so not just the software. So you'll see here I walk up to the machine and enter my user login. Same steps as before for this stage. We'll see the baseline user recommendation profile. You'll see there's an out-of-stock product, which is automatically filtered to the end there. So I'll enter my peanut allergy, and then this will essentially update the recommendations, slotting the allergen items to the right. And I'll go ahead and run Goldfish. You'll see here it's dispensed, and I open the dispensing part here, get my Goldfish, so I'm incredibly happy that I have them now. And then we'll go ahead and simulate going back into the machine another time. So since I love the Goldfish, I'm going to give this a thumbs up rating, and this will actually update the percentage match for the Goldfish here. And
Thank you so much for watching.